Hi, welcome to this video. I'm Liam, this is William. So this video, what we're going to do is we're going to demonstrate how we calculate the compressive strength for a concrete cube. So we're going to be using this machine. So this is the compression machine. So this comprises of two pistons. So we've got this lower platen which basically raises up so we can set the rate and the load that's applied to the relevant standards. So in our case, the standards we're going to be referring to is BS 12390. So this dictates for the cubes that we're going to be looking at, should be about 100mm by 100mm in plan. For that particular cube size, as defined in British standards, that's going to have a pace rate of 6 kilonewtons per second. So what that means is that lower platen that you see here in the machine is going to raise up and apply a force of 6 kilonewtons per second to the concrete cube whilst it's being tested. So what it's going to do is it's going to keep applying that load until the concrete fails and shears. So what we've got is we've got the cubes. They've been in this curing tank now for 28 days. So I've got two cubes here. So we'll start with the first one. So just looking at it there's no kind of major defects obvious from that sample. So what we do is we just check the dimensions just to make sure there's no deviations from the standard. So we'll just check that just now. So that's 100mm. 100. Also do that with calipers. 100. Yeah, so you could do that with vernier calipers, which will give you a more accurate result. However, for the purposes of this video today, we'll just use the steel rule. So the cube reference, the first row that we've got on our table, that's just a reference so we can identify when the cube was made and what it kind of relates to. So in our case, this is just for testing purposes. It doesn't actually refer to a particular element within a structure. So if it did, you could do that in your cube reference row. So what we're going to do is we're going to position this cube now in the centre of the bottom platen, and I'm going to rotate it so that we're not testing against the face of which the cube was made. So we turn it through 90 degrees, so that should give us hopefully a truer set of results at the end of the day. So I'll pop this in here just now, and centre it as best we can, and then close the door. That's that now secured in there. And then just use this. This is an automatic testing machine, so it does everything for you. No need to change anything once it's set. So what I've done is I've input on the screen here. You can see I've put in the dimensions to the relevant standard, and also set the pace rate there to 6 kilonewtons per second. So that's now good to go. So what we do is we just basically escape back through the menus. And then test the cube itself. So what we do now is we just hit the green button to go, and then that will start applying the load at that given set rate. So as we can see, we're now getting a readout here with the force, so that's increasing. The machine's still applying that rate of 6 kilonewtons per second. So what we'll see in a moment, these figures will keep rising and then they'll drop off, start falling, and at that point that's when the cube is deemed to have failed. So it's reached its optimum compressive strength. You can see now we've reached the peak and it's gone down, and there's our set of results. So for this particular cube, we've got our maximum load was 258.9 kilonewtons. Which gives us a compressive stress of 25.89 newtons per millimeter squared. So that's that cube tested now, so it should have failed. Take it out and have a wee look just to see what it looks like. So we'll break off some of these elements and have a look and see how it's failed. So ideally what you'd be looking for is that angle of approximately 45 degrees in towards the centre of the cube. So in this case you can see it has. So basically it's almost like a kind of apple core effect. You can see as well the aggregate's actually sheared here. It's sheared right through the aggregate rather than the bond that's around it. So that's not what we're looking for. That's aggregates which are not very strong. So that's kind of typical. That's what you would want to expect, is that kind of almost apple core effect. So that's a kind of normal failure. So that's about it for this first sample. So what we'll do now is we'll test the second one, and then we can do a comparison of the results. So welcome back. So what we're going to do now is we're going to test the second cube. So we tested the first one. So again, we've got the second cube in the curing tank. So it's been here for the last 28 days curing. So what we'll do now is we'll just dry it off, and we'll weigh it to get its mass. So then that will allow us then to calculate the density. So this is cube number 2. So the mass of cube 2 is 2.314 kilograms. And again, check for any defects, but everything seems to look okay. There's nothing glaringly obvious, any cracks or deviations in the surface. So what we'll do again, we'll just measure the dimensions to make sure they're compliant with the standards. So 100 and by 100. This one's actually just over 100, so this is about 101 for the height. So to get it more accurate, you would normally use vernier calipers. However, we don't have it on hand today for this video, so use a steel rule. So same as before, we'll just position it in the middle of the machine as best we can. Again, testing against one of the edges perpendicular to the surface it was made on. So pop that in there like so. Centralise it and then close the door. And then it's already preset, So we'll keep the settings the same. So again, it's going to be 6 kilonewtons per second. It's going to be the rate at which that lower platen is going to raise up. So that's good to go. So what I'm going to do now is just press the green button. The machine will start, and then we'll see our force increasing as the cube is being tested. So the cube itself has not quite reached the top platen. So there'll be a change in sound, so there you go, you can hear the slight change in tone. And we can see our force is now increasing.
Expecting something similar to the last one, given the way they were made and the time they were made.
So it is still increasing, you can see here. So that's it now, you can see it's starting to decrease again, so it's reached its optimum. And there's our results now on the screen.
Those results are for 100 by 100 by 100.
Yeah, so these results are for cube dimension 100 by 100 by 100. So in our case, the face that we've tested on is 100 by 101. So we'll need to alter the value that we've got here. So to calculate the compressive strength, it's going to be force over area. So our force at failure in this case is our 278.8 kilonewtons. So we need to multiply that by 1,000 to convert from kilonewtons to newtons. And then our area at the bottom should be 0.1 by 0.1101. So that should be, oh, that's the volume, that's my area. Okay. So if we do that calculation, that will give us our compressive strength for the cube in newtons per millimeter squared, or megapascals. So you can see for this sample, so the second cube, we've achieved a compressive strength of 27.604 megapascals, or newtons per millimeter squared. So what we can do now, we've got two sets of results. So what we'll do is we'll just take an average, and that will determine our compressive strength for this particular sample of concrete that we've made. So again, what we'll do is we'll just take it out of the machine, and we'll have a look, and William will explain then the different failure types and what would be deemed as acceptable, and which would be deemed as non-compliant. So again, you can see all the corners, etc., are relatively loose, they're just all broken away. So this one's slightly more intact than the first one. You can see here, so this is the top surface, so basically a cube mould. So these are what they were formed in. So this here is actually the top surface, which it was made. You can see there's a slight crack then just appeared along that surface once it's been tested. So I'm not sure, that could be just some defects from the way the cube was moulded, or it could be to do with the strength. So it looks like it's some form of kind of latence on the top, with aggregates kind of separated from the finer materials in this case.
probably not mixed well enough.
So that's our cube number 2. So cube number 1, cube number 2.
Similar. If you look at the apple core.
So we see how that looks now compared to the
So if we
relevant
go
standards.
to the British Standards 12390 and you go down to section 8, section 9, you can see that you've got acceptable or satisfactory failure types of the cube. And you can see the ones that we've got look like the one in the middle. Looks like the apple course. This is sample 1. We've got sample 2 over here. You compare that to unsatisfactory failure types of cube specimens. So you can see here we've got tensile cracking in various forms on the face of the cube. Our samples here don't have that. We've also got unsatisfactory where they've spalled away, like peeled away on one corner or one edge or one corner, one face. Ours is fairly uniform and consistent. So you'd say that would be a satisfactory failure. It's obviously got quite a lot of it still intact, so it wouldn't be an explosive failure, and we could possibly still test this and see if there's any residual strength left, and obviously we'd need to calculate the area that would be testing, so that when we put our force through it, we'll see what the compressive strength is left in that. So maybe do that just now. So we're going to test the residual compressive strength that's remaining in this cube. This is it's obviously experienced failure, but there's still some strength that's left here within it. So we'll put this back into the machine, and we'll see what force we can get within it. First of all, we'll take a reading, and you still see we've got an area 100 by 100 on that surface. This is for cube 1. Center that. Close the door. So put this back to the start. And set our machine off. Last time we had 258. Last time we had 258. This time we got 137.2 kilonewtons of failure. So let's put that in brackets here. So just over half that's left compared to the initial test we had for the residual strength for that one. We'll just take this out, see what that looks like. You can see here we've got significant cracking and failure of the sample. There's not much left with that. failure lines all over. You can see that that's could come straight away, come off.